Julia, can you grab one of those red books? I think maybe even a couple. That'll help me. I can stand up. Thanks. Appreciate it. There. Huh? What's going on?
There you go. Oh.
Question? Yep.
Don't get lost again.
Do you get lost? I get lost all the time. Let me know if I go off screen or whatever. It's kind of hard to tell. Okay, so I'm going to go over the example problem, page 44. This is all rotational equilibrium.
Are you recording it?
Yep. Yeah, I'm recording it. So, rotational always has to do with the beam. That's your clue. Has to do with the beam, as in this problem here. I know, man. It took me a lot of practice. Okay. That's your pivot. How do I know? Because it's attached to the wall. That's your clue. There's a hinge there. That's your pivot. You're measuring your distance from that little triangle. Okay. So first distance. We'll use the same notation. That's L. That makes... I'm going to probably relabel some of this, keep it simple. That's your FG. That's acting at half the distance. It's always the case. The weight of the beam always acting at half the distance. Okay, so you've got the force acting at the hinge. There's two forces there. There's a force acting up, and they call it FV. And then there's a little force acting to the right. They call that FH. Okay, no torque. No torque at the hinge. Because the distance is 0. It's always the case. No torque. There's forces, but no torque. There's a force acting down here due to the weight. We know what that value is. It's 100. And I'm just going to recolor this. This will come in handy later. Any downwards force will be yellow. Sideways force will make purple. Helps. We'll see later. There's also a force acting at an angle. I'll just call that, we'll go with what they say. This is F1. It's acting at an angle of 30 degrees. Okay. So what is F1? That's the question. So you see that it's a beam. That's your clue that you should start off with the condition for rotational equilibrium. All the torques have to balance. Just another way of saying this says all the torques add up to 0. Another way of saying it is torques balance. Same thing. So which torques? This time we'll label it to make more. We'll call this the torque due to F1. We'll call that tau 1, torque 1. Torque due to the 100 Newton force, we'll call that torque 2. And the torque due to the weight, we'll call that torque G. G being the force of gravity acting at the center. What does it mean to say this? Or what does this state here? It means the following. First of all, let's look at the directions that the torques would. Look at that. Okay. Focus on that. That torque is due to this force F1. Forget about the other forces. We have to look at each of these forces individually to tell or figure out what the direction is. You have to ask yourself, you ponder the question, which direction would the beam rotate if this force 1 was allowed to act all by itself? So if it kept pulling, which way would it rotate the beam? Would it rotate it this way? Or would it rotate it this way? This is counterclockwise, this is clockwise. If it were to pull, up in this direction, there's an upwards component here. Which direction would it rotate the beam? Counterclockwise. Okay? Any counterclockwise torque is considered to be positive. So when we say the torques balance, another way of saying that is okay, we'll put the counterclockwise torque on the left. What about the other forces? Which way would they rotate the beam? Which way would FG rotate the beam if it were to act all by itself? And remember, the pivot is kept in place, doesn't move. The beam can rotate, but the pivot doesn't move. Clockwise, which we'll take to be negative. Same thing for torque 2. Same thing for this 100 Newton force. It would rotate the beam this way. Rotate it this way, which again we'll take as negative. Opposite direction to torque 1. Okay? So what do I mean by saying that these torques balance? I'm just saying rearrange this equation here comes from this, adding up all the torques, making the clockwise torques negative. To say that they balance just means when you rearrange the equation, you get this. When you put all the negative terms on the right, you get this. I'm just adding TG and T2 to the left and the right. That's it. Another way of saying the same thing. The torques balance or the torques add up to 0. It's the same thing. If you take into account the proper sign. Clockwise rotation is negative. Okay, so you can write it either way. I'll probably tend to stick with the second one, this one here. Okay, so let's just, I'm going to make a copy of it. You can rewrite it. Put it here. I'm going to do it for you in a second here, but fill in the expressions for each of these torques. Don't tell me, but fill them in according to the F1, FG, 100, and the L and the 1/2 L. Fill it in. That's your starting equation. T1 or torque 1 is equal to torque G plus torque 2. Now fill it in terms of the forces. Okay, so let's look at this. What's my torque 1 here? Torque is always force. Yeah, sine in this case of 30, which we'll simplify in a second, times the total distance, which I call L. Okay? Now let's simplify this. Sine of 30 is 1/2. F1 times L. I would circle it. Circle it. That's your first expression.
So where does the 1/2 go?
We'll come back. We'll come to that in a second here. I'm going to erase this. I need the room. What's the expression for FG? Torque of G is FG times the sine. It's a perpendicular angle because the beam is level. It's the sine of 90. There's your 1/2 L. Here's your 1/2 L. Simplify it. FG is just mg. Does it give you the mass? No, it gives you the weight. We'll just keep it as FG. If they gave you the mass, you'd turn it into mg. Sine of 90 is 1, so this reduces it just 1/2 L. Circle it. You have to come back to it. Third expression. Torque 2. 100 times sine of 90 times the total distance L. Which simplifies, this is 1 to 100 times L. Circle it. Now you can fill in your expressions. And fill them in. If you didn't do it correctly, fill it in. See if you can simplify the expression. Don't tell me, but see if you can factor something out. By the way, this should be a 1/2 here, right? Should be a 1/2 here. Sine of 30 is a half. I'm just going to draw the L's in as yellow. Because the L is a common factor to each term, so that means you can cancel it out. Okay. Multiply both sides by 2. And you solve for F1? Yeah, because we got FG. FG is given 25 newtons. That's it. Just give an absolute value. Not interested in direction yet. So. That's the first part. This is part 1. You can call it A. Did they label it? Yeah, that's A. Part A. Part B. There's always, if it's a more complicated torque problem, there's always a part A and B. Part A, for us, will always be starting with the torque. Balance the torques. Balance the torques. Part B, if there is a part B, is solve for the horizontal and vertical forces. That's what the hinge, at the hinge. So these forces here. Solve for FH, FV. That's part B. Won't always be a part B, but in a more complicated one there is. Okay, I'm going to need this diagram, so I know you have to redraw it, but I'm going to copy it. I need, you know what? I need it bigger. Whoa. Serves me right. Yeah. There you go. What the heck? Whoa. Huh. Okay. So I am going to outline the components here. That I'm going to call F1, X. And then the component here is a vertical, so it's yellow. That I'm going to call F1, Y. Now look what I did here. I assumed I pointed the direction of FH to the right. We're not sure. In some cases it's to the right, some cases it's to the left. I can tell just by looking at F1x, because they must balance, FH actually must point to the left. So let's correct that. That's your FH. Okay, so I color coordinated it. Start with the X's and then work with the Y's. Write down what you don't tell me, but, and again, I would do it in pencil in case you make a mistake. Up to you, or leave space so you can write the correct expression if you make a mistake. Write down the expressions of the forces in the X and the Y. How do you think they relate using those expressions there, those notations? FH, FV. This one here is FG. Start with the X expression and then write the Y. How do you think it should be spelled out? And now we're not interested in balancing torques. We're interested in balancing forces. How do you think the expression should be spelled out to balance the forces? It's not moving up or down, right? It's just sitting there. So not only must it be under rotational equilibrium, it must also be in translational equilibrium as well. So this expression for the forces we're going to write out next. It applies in the X and the Y. Start with X. Can you see the purple? Is that okay? It's not too bad. Okay. So start with, write this equation down first. Even though it's a little bit formal, we need formality so I can see clearly, understand. By writing that down, you're telling me that force is balanced in a very short notation. It's just a short way of saying that force is balanced. Now, what is that reduced to in terms of these forces here? The FH and the F1, the F1x. What can you tell me about those forces? When I say they balance, how would you write that out? Yeah.
So it would be F1x minus F8 equals 0.
Good. So you start off with that. I'll put FH first. Doesn't matter. I see what you're saying because FH is to the left. Sure. I'm going to do it that way. F1x minus FH. FHx to the left, so it's subtracted. Good. You can write it out like this. Add FH to both sides. You get that equation, which is essentially saying what I said earlier. The force is balanced. So you can go to this equation like Cam did, or you can go directly to this. It's fine with me. But just keep in mind, some people are a little more formal. They may expect all the steps. But essentially, it's this. Essentially, you get to this equation here. The forces balance each other. That's a simplified version of adding up all the forces to 0. Okay. So let's go further. We don't have an answer for FH yet. What's F1x? F1x is just F1 times something equal to FH. Fill that something in. Hypotenuse, F1 times. Yeah.
30.
That's it. And we have the F1. We just figured it out there. 225. Okay. So that works out to be 195. Okay. And yes, it's in the direction that I said. It has to be to balance the F1X. FH has to be to the left. So you have to include it either in written form, either put that to the left, or you can put a negative if you want. Either one I'll accept. Or at the very least, include it in the diagram. You have to show me you understand that. Okay. Second equation. Yellow equation. What does that mean? It means add up all the forces. They should add up to 0. So let's do that. Any upwards forces are positive. We have to add the FV to the F1Y. And any downwards forces are subtracted. And that must all add up to 0. What's another way of writing that? The forces balance. Upwards forces balance the downwards forces. You want to skip right to this? It's fine. Just include this to begin with. If you want to skip to this, that's fine. Just be aware some profs or teachers might expect the second step, so be aware of it. Can we solve for FV?
Yes.
Yeah, we're almost there. FV, what's F1Y? Just F1 times the sine. Go back to this. This is the opposite side. Let's start filling in values. Do we have FG? Yeah. FG is 25. Do we have F1? Yeah, we figured it out. Half, sine 30 is a half. That's it. Out of 25 minus 112.5. Okay. So, if you're asked to solve for the force on the hinge, that means there's a part B. And what's the difference between part B and A is in part B, you have to use the equation for the forces. To use these equations here. Part B, use the equation for the forces. Part A, use the equations for torque. I erased it, but I've gone over the steps earlier. You start off with that, which in this particular case simplifies to that. Okay, so how do you know whether it's a torque problem or not? You're looking for a beam. If there's a beam involved, then set up the equation for torque. A lot of steps. Okay, so you've got a couple more minutes here. I'll post this later. We're going to go over another example. I need, yeah, I'll give you